When you push a commercial aircraft above 35,000 feet, the world below disappears. There are no highways, no coastlines, and no visual landmarks to guide you through an endless expanse of white clouds. Up here, a pilot's entire reality is constructed from mathematical abstractions. You rely completely on precise angular directions and absolute global coordinates to know exactly where you are. Relying on the basic high school geography concept of a perfectly round Earth to plot these coordinates will lead to significant navigational errors. To clear your DGCA exams and operate high-performance aircraft, you have to discard that simplified model. You must upgrade your mindset to the strict mathematical precision required for aeronautical navigation. In this session, we are going to decode the true shape of the planet, the mechanics of the WGS-84 standard, and the universal rules governing how aviation calculates direction. True airmanship begins right here, by understanding exactly how to locate yourself on a mathematically imperfect planet. So, is the Earth actually a perfect sphere? The short answer is no. As the planet spins on its axis, the resulting centrifugal force constantly pulls its mass outward. This rotation causes the shape to flatten at the poles and bulge at the equator, creating an oblate spheroid. Because of this distortion, the polar distance is exactly 43 kilometers less than the equatorial diameter. In aviation units, that equals exactly 23 nautical miles. This creates a polar compression ratio of 1/300, or 0.3%, a specific metric frequently tested on DGCA exams. While a student pilot plotting a short cross-country route on a paper map can treat the Earth as a perfect sphere for simplicity, precision computer systems cannot. To navigate this oblate spheroid accurately, modern avionics use a standardized mathematical model called the World Geodetic System 1984, or WGS-84. WGS-84 is the mandatory global datum adopted by the International Civil Aviation Organization. It is the exact structural blueprint that your aircraft's GPS uses to calculate position. Without factoring in the specific oblate flattening detailed by WGS-84, every satellite navigation fix you receive would be structurally flawed. Knowing the true shape of the Earth leads to the next problem. How do we definitively plot a location on the surface of a spinning, bulging sphere? A traditional flat graph using linear x and y coordinates fails when wrapped around a curved three-dimensional object. The solution relies on angular measurement from two perpendicular datum lines. First is latitude, the angle measured north or south from the equator, from 0 to 90 degrees at the poles. Second is longitude, measured east or west from the prime meridian, to 180 degrees. In aviation, there is an unbreakable convention for expressing these coordinates. Latitude is always stated and written first. For example, a waypoint would be listed as 41 degrees north, followed by 074 degrees west. This intersecting angular grid, known as the graticule, gives pilots an unambiguous global address system that remains strictly accurate regardless of the terrain or the aircraft's altitude. That angular grid seems complete, but the Earth's polar compression creates a dangerous mathematical trap for unwary navigators. Because the planet is squashed, a plumb line dropped perpendicular to the ground will not hit the Earth's exact geometric center. This creates two ways to measure latitude. Geocentric latitude calculates the angle measured directly from the Earth's true geometric center. Geodetic latitude calculates the angle using the perpendicular plumb line to the ellipsoid surface. Practical navigation systems rely exclusively on geodetic latitude. This divergence between the lines reaches its absolute maximum at exactly 45 degrees north or south. At that exact latitude, the difference between geocentric and geodetic measurement is exactly 11.6 minutes of arc. Because 1 minute of latitude equals 1 nautical mile, mixing up these two models would inject a position error of 11.6 nautical miles into your flight calculations. Being off by nearly 12 miles while attempting to line up an instrument approach in bad weather is catastrophic. This is why theoretical geocentric models are left to astronomers, while pilots trust the geodetic measurements mapped to the true oblate surface. Once you have locked in your exact geodetic position, the task shifts entirely to defining where you are going. Aviation dictates direction using the sexagesimal system, a base 60 mathematical standard that measures angles in degrees, counting clockwise from a fixed datum. On the left compass rose, true north at 000 degrees is the datum. East is the direction the planet spins. On the right is the three-figure rule. Every direction must contain exactly 3 digits. You never declare a heading as 27 degrees. A dropped syllable could make 27 sound like 270. Say 027, eliminating ambiguity. The panel at the bottom right outlines reciprocal headings. You add 180 to your current heading if under 180 degrees, and subtract 180 if over. The three-figure rule functions as a global safety standard, ensuring air traffic control and pilots maintain identical mental models during high-stakes maneuvers. All of these complex angular coordinates and directional rules ultimately translate to raw physical distance over the ground. The foundational rule tying this system together is that 1 minute of arc along a great circle equals exactly 1 nautical mile, or 1,852 meters. A great circle is any circle drawn on the globe whose center matches the exact geometric center of the Earth. Navigating along one provides the absolute shortest path between 2 points. The equator is a great circle, and so are all the vertical meridians of longitude. However, all other horizontal parallels of latitude do not bisect the Earth's center, making them longer, inefficient, small circles. Plotting long-haul routes along great circles rather than flat compass lines is how flight dispatchers minimize time in the air and save airlines thousands of tons of fuel every year. To succeed in navigation, you must lock in these facts. The Earth is an oblate spheroid. GPS relies on WGS-84. Aviation maps use geodetic latitude, and the maximum anomaly of 11.6 minutes occurs exactly at 45 degrees north and south. Professional navigation requires a highly precise mindset that filters out basic geographic assumptions to calculate pure mathematical reality. Mastering the mathematical certainty of the graticule, the oblate spheroid, and the sexagesimal system is your very first definitive step towards successfully earning the 4 gold stripes of a true commercial commander.